So in this video, we'll be going through the example of a skier being pulled up a slope. So we're told that we have a 50 kilogram skier. It's being pulled up a 50 meter on the slope of 30 degrees. It's being pulled at a constant speed. The tension is 280 newtons and the frictional force is 35 newtons. Kinetic frictional force opposing the motion. So we're asked to draw a free body diagram, and then we're asked to draw the work diagrams and calculate the work for each force to eventually determine the net work. So let's start by defining our axes so we can draw our free body diagram. I'm going to choose upwards to be the positive y and to the right to be the positive x direction. Now we can draw our free body diagram. We start with our non-contact force, which is the weight force, and that's pointing downwards. Then we know that the slope is pushing up on the skier, opposing some of that weight force. So we'll draw that in the positive y direction. That's F sub n. We have a tension force being applied by the tow rope on the skier, and that's going to be pointed up the slope, so in the positive x direction. And then we have the frictional force, the kinetic frictional force, that's opposing the motion, so that will be pointed down the slope in the negative x direction. So that is little f sub k for kinetic frictional force. So the weight force is the only force that's not in purely either the y or x direction. So let's get an angle associated with that weight force. So we have the incline here, that's 30 degrees. And here is the 90 angle. So here, I'm going to start by drawing my y component of weight and then my x component of weight. We have the 90 here. So what you do is you just match up the 90s, and that lets you know that that angle right in here, really small, theta is equal to 30 degrees. So now that we've defined all of our forces, we can fill out this table. Just going down, F sub n. For the normal force, we have the tension force, we have the kinetic frictional force, and then we have the weight force. So that 4 forces, we'll need 4 work diagrams, and we'll need to calculate the work for each. So now we'll draw our work diagrams. Remember that the displacement vector is going to be along this positive x direction, d here. And that's because the skier is going up the slope. So starting with the normal force, we have a normal force in the positive y direction. We have a displacement in the positive x direction. So those two are going to be perpendicular to each other. So we have F sub n. We have d. So those are going to be perpendicular. For the tension, we've got T, the tension, and the displacement D in the same direction. So I've got tension here. And then I've got displacement here. So that's going to be theta is equal to 0 degrees. Up here is theta is equal to 90 degrees. The kinetic friction now. So we've got displacement in the positive x direction. We've got kinetic friction in the negative x direction. F sub k. And we've got d. So the angle between them, this whole angle right here, theta is equal to 180 degrees. So now comes the weight one. This is the harder of the four. So I'm going to draw it like we have on our free body diagram, with a weight being pointed downwards, W, and then we've got D pointed up at an angle, D. So what we need to know, when you can think of it, we've got the y-axis like that. So now what we need to do is we need to figure out what that angle is between D and W, so this whole angle. We know what this one is, this smaller one. That's 30 degrees based off of our free body diagram. And then the rest of the angle, we know that D lies along the x-axis. And then I drew the y-axis in there, and those two are perpendicular to each other. So that angle right here is just 90 degrees. So theta is equal to 30 plus 90, which is 120 degrees. So the weight force and the displacement have an angle of 120 degrees between them. So now let's calculate the work done on the skier by each individual force. Let's recall that work is equal to the magnitude of the force multiplied by the magnitude of the displacement multiplied by the cosine of the angle between them. So for the work done by the normal force, we have the normal force times the displacement times cosine of 90 degrees. We know that cosine of 90 degrees is just 0. So the work done by the normal force is 0. For tension, we have tension's 280 newtons multiplied by 50 meters times the cosine of the angle between them, which is 0. Cosine of 0 degrees is just 1. So we end up with 14,000 Newton meters or joules. Moving on, for the kinetic friction, we have a force of 35 newtons multiplied by 50 meters times cosine of the angle between them, which is 180 degrees. So instead of 1, it is -1 since it's 180 degrees. And so that's equal to -1,750 Newton meters or joules. Then rounding out with weight, we have weight's equal to mg. So that's equal to 490 newtons multiplied by 50 meters times cosine of the angle between them, which is 120 degrees. Cosine of 120 is equal to -1/2. So we end up with an answer of 12,250 joules, negative. So now we're asked to calculate the net work by adding up the work done by each individual force. And let's take a moment to think about what do we expect the answer to be. So our system is the skier. The skier is at a constant speed. So the change in kinetic energy of the skier is going to be 0. So we expect the net work as a result to be 0. So let's see if that works out. So the normal force is, the work done by the normal force is 0, plus the work done by tension, which is 14,000 joules, plus a -1,750 joules by the work done by the kinetic friction, plus a negative 12,250 joules, the work done by gravity. Add those up, and you find that the net work is 0, as expected.